Hello. So today we're going to talk about telescoping products and logarithms, right? So we are, usually used to telescoping series, right? Some summations. But when you want to telescope a product, right, the pi notation basically, there is usually some kind of pattern that is being formed, right, which helps us to easily evaluate that given product, telescope the product. So yeah, and this question will also involve logarithms. So kind of telescoping logarithms actually. So yeah, let's just get started. This is the problem number 7 from the AIME exam, AIME 2 in 2014. So AIME has basically, let's just put it like two components, AIME 1 and AIME 2. You can take any one of them, you can't take both. So this is the AIME 2 in the year 2014 and problem number 7. And in this video, we're going to talk about summation and telescopic products, logarithms and their properties, book suggestions for National Math Olympiads, and at the end, a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so what does it say? So they've told us like a function f of x is x squared plus 3x plus 2 raised to the power cosine pi x. Okay, that's pi 3.1415 and so on. And they're asking us to find the sum of all positive integers n for which this condition satisfies. Okay, so let's maybe first investigate this condition and then we'll try to explore what the function is. Okay, so we have this summation from k is equal to 1 to n of logarithm base 10 fk. Now the modulus is 1, so this thing can be either plus or minus 1, right? It can be plus 1 or minus 1 because the modulus is 1. Okay, great. Well, if you just going to expand this summation, what do you get? So you'll get log base 10 f1 plus log base 10 f2, and this is obviously, all the way up to log base 10 of f of n, right? This can be either 1 or minus 1. And this is a very interesting property with logarithms. I'm pretty sure you've heard of this. So log a plus log b so happens to be log of a times b. So you can kind of, merge this into a single logarithm. And this actually, you can generalize this. So log a plus log b plus log c, for instance, would be log ABC and so on and so forth. So whenever you have addition of logs, if you want them to merge it into a single log, it just becomes log of the product, right? So over here, with the given equation that we have, this equation, how can I maybe like merge that into? It's pretty easy. So this just becomes log with the base 10, f1 times f2 times f3, all the way up till fn. All of this obviously in a single logarithm, that is 1 or minus 1. Now, obviously, if we have, let's say, log any number a to the base b is equal to some number c, then that essentially implies that b raised to the power c is equal to a. And these are equivalent expressions. So basically, the thing inside over here, this f1 times f2 all the way up to fn can either be 10 raised to the power 1 or 10 raised to the power minus 1. Basically 10 or 1 by 10. Right, so we have this very important result that f1 times f2 dot 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 all the way up to fn, the product will either be 10 or 1 by 10. Okay, but till now we've really only been dealing with what we need to find, right? We haven't really dug into the question, right? So what is this f? So they had given us a function, right? F of x is x squared plus 3x plus 2 raised to the power cosine pi x. Now let's just maybe try and figure out certain values. So for example, let's just analyze this cosine pi x, right? Let's just analyze this part because that is the relatively interesting part, right? The rest is just algebraic, it's just polynomial. So if I plug in maybe x equals to 1, I'll get cosine pi, right, which is minus 1. If I plug in x equals to 2, I'll get cosine 2 pi, which so happens to be 1. If I plug in x equal to 3, I'll get cosine 3 pi, which happens to be minus 1. If I plug in x equal to 4, I'll get cosine 4 pi, which is again 1. So if you actually notice something, and this obviously goes on and on, right? If you actually notice something, if x is odd, then cosine pi times x becomes -1. That's kind of observation, you know. Whenever it's odd, we get a negative sign. And whenever it's even, we get a positive sign. So that's the only two outcomes possible. Right? We get +1. Okay, that's great. So now what we're going to do is now we're just going to analyze this function f of x. Now, f of x, I can just factorize this as x plus 1, x plus 2. You don't need to, but you know, calculation becomes easier. Raised to the power cosine pi x. You know, and I kind of this analysis of pi x so that just the calculation is easy. At the end of the day, we want to find f1, f2, f3, all the way up to fn and just see how that works out, right? So let me find out the first few values. So for example, if I just plug in x equal to 1, I get f1, right? That is 2 times 3 raised to the power -1, which is 1 by 2 times 3. Yeah, pretty clear. Just plugging in values. If I plug in f of 2, x at 2, I get 4 times 3. And you can compute this yourself. f3 you will get 1 by 5 times 4. f4 you will get 6 times 5, and so on and so forth. I essentially just computed the first few values, and there's a reason I did that. Because you see, we have this kind of result that the product of certain values of f, right? f1, f2, f3, all the way to fn. Right? And we need to find at what value of n this reaches 10 or -10. So, you know, just to kind of explore this, just to kind of observe what is exactly happening, let's just consider the product, right? So f1, there was obviously 1 by 2 times 3. Okay, great. What was f1 times f2? Well, this so happens to be 1 by 2 times 3 into 3 times 4. So this is obviously 4 by 2, right? What about f1 times f2 times f3? What will this be? Well, this so happens to be 1 by 2 times 5, right? Which is actually 1 by 10. So n is equal to 3 is a valid solution because we want to find the values of n for which we get 10 or 1 by 10. So n is equal to 3 is a valid solution. We're getting 1 by 10. Okay. What next? Well, maybe let's consider f1, f2, f3 and f4 as well. Well, this so happens to be 6 by 2, right? And if I just maybe consider one more term, so I'll take it up till 5 over here, I'll get something like 1 by 2 times 7. They actually notice something over here. If the last term is odd, so 1, 3, 5, 7, 9, blah, 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 we get 1 divided by 2 times something. Now that something can be whatever. For example, if we have 3 over here, again odd, last term is odd, we get 1 by 2 times something, right? Here also we have 1 by 2 times something. Again, if we have f1, which is again odd, we have 1 by 2 times something. So basically when the last term is odd, right? So when we have f of odd number at the last term, we get 1 by 2 times something. I mean something very little, it can be anything. And whenever we have even, whenever we have f of some even number as the last term, basically when n is even, we get something divided by 2. And let me just show you this as well. So 4 is even, like I was saying 2, 4, 6, you will have something which is 6 divided by 2. When I had f2, 2 is even number as the last term, n is equal to 2, I got 4 divided by 2. So something divided by 2, right? So when it's even, it's something divided by 2, and when it's odd, it is 1 by 2 times something. So now at n equal to 2, we got 4 by 2. Right? N equal to 2, where it was, there we go. N equal to 2, f1 times f2 is 4 by 2. And this is obviously, here what I'm writing is f1 times f2 all the way up to fn, the product. Now at n is equal to 4, we got 6 by 2, right? N equal to 6, we got 8 by 2. This is what we had computed. These 3 values I had myself computed, right? And do you notice some pattern over here? So what do we actually need to find? So we need to find when will this be 20 by 2, right? When will this, actually on the right hand side, will become 20 by 2? When will this happen? Because we need it to be 10, right? And 20 by 2 is 10. I'm sorry about that. So we need it to be 10, right? And 20 by 2 is 10. So how do we get 10? So what pattern is being followed over here, right? Well, it's a very straightforward pattern. We have 2, 4. We have 4, 6. We have 6, 8. So just for instance, n is equal to 8 will give me 10 by 2, right? And this will obviously go on and on. right? This will go on and on. This pattern will go on and on. And when we have n is equal to 18, we will have 18 plus 2, 20 divided by 2, which will give me 10. This is a very straightforward pattern over here. Now, what is happening? At n equals to 3, we have, f1 times f2 all the way till fn. In this case, obviously, it is f1 times f2 times f3 becomes 1 by 10. Now at n equals to 18, similarly, f1 times f2 all the way till fn, the product becomes 10. So these two values satisfy. But the question then arises, are they the only values that satisfy? Well, the answer would be yes, because what is happening over here? So for example, when we considering it as an even number, right? Something divided by 2. Now when n increases, this something is also increasing. Because if you see over here, we have 2, n is equal to 2, we get 4 by 2, which is 2. We get n is equal to 4, we get 3. When n is equal to 6, we get 4. Right? So it's increasing. It's increasing with n. When n is equal to 8, we got 5. When n is equal to 18, we got 10. So it's kind of increasing. So no matter what other n's we have, for example 20, 40, 60, is obviously going to be greater than 10. So 10 as a value is never going to be repeated. Right? So for 10, this is the only solution, n is equal to 18. And how about for this 1 by 10? And for 1 by 10, kind of by a similar assertion, 1 by 10 is the only value. Because what is happening, we had 1 by 2 times something. So as n keeps on increasing, this something keeps on increasing. So this total value, f1 times f2, we put it this way, f1 times f2 all the way up to fn, this also keeps on decreasing. And I think that's also very clear. Because if you look at f1, we had 1 by 6, right? If you look at f3, we had 1 by 10. It's kind of decreasing. Right? 1 by 10 is 0.1. And f5, we got 1 by 14, which is again decreasing. Denominator is increasing, the number is decreasing. So again, as n increases, the term will keep on decreasing. The entire thing will keep on decreasing. And you'll never, ever get 1 by 10 again. So basically, the assertion is that these two are the only solutions. Right? N is equal to 3 and n is equal to 18, the only solution. Therefore, sum of solutions just happens to be 3 plus 18, which is 21, and that is the answer. So yes, this was very, very small and nice question involving telescoping products, right? And I hope you learned something from that. Okay, so we have some book suggestions for USAMO, USAJMO, or AIME. Elementary Number Theory by David Burton, Problems on Strategies by Arthur and Gell, Functional Equation by Venkatachala, Problems in Plane Geometry by Sharagan, Elementary Number Theory by Sierpinski, Graph Theory by Harari, and Combinatorics by Brualdi. Okay, so at the end we have a similar challenging problem, and I want to evaluate this summation, So maybe try it out and actually also think, does this actually converge or diverge? So there's something about summations. They do not necessarily always converge, right? So maybe just try and look at if this actually converges or diverges. For those of you who have studied tests of convergence or divergence in integral calculus, this might be very easy. But maybe just try it out using normal algebraic methods. And until then, I'll see you in the next video. Thank you very much and bye-bye.
The programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.